Now, this network, because it's a very early piece of work, which we, did by ourselves. We didn't really look into what other companies. We took up, kind of we experimented with, multiple layers, and we found that a 4-layer network was giving a reasonable set of results. Then, after this, we went to the transfer. So, as you all know, an existing model, trained model, with the weights already you picked up from that in your test area. And then you further train the network with your images, set of images, and try to find those ways to suit your need. That is what you say about the, so transferring the knowledge learned from model from one domain to another. Okay, I'm going to show the model that we use. And obviously, when you don't have access to compute time, which is typically the case with many universities, you can't have a data center. And then whatever Google Colab kind of tool that you want to use, environment that you want to use, if you go for a free version, then you have to spend a lot of time and kind of thing. But you want to go for Colab Pro and try to do faster, then you have to pay. And sometimes you get into that kind of situations, so when you are not an extremely rich university, you don't have endowments, that kind of thing, you have to survive only on the tuition. You cannot really set up large computing facilities that will facilitate you to work, kind of thing. So therefore, typically in our situation, because the transfer learning models help us to reduce the overall time for training that data. So that means the process of training are pre-trained, right? So transfer learning model, there is an existing model with a set of weights, and then therefore you use those pre-trained weights, and with the back propagation of your fully connected dense layer, you are able to kind of fine-tune the weights in your case. So that means you start training with your images, and then try to modify those weights, which will eventually help you to classify. So therefore, whichever transfer learning model or pre-trained model, you free those layers and then fully connected replace with the newly, in your case. So you basically transferring the knowledge from an existing model onto your way of doing things. For you have your fully connected dense network that will have weights in line, in tune to whatever images that you provide. I'll just show you. So how do these pre-trained models come into picture? So what you essentially have, if you look at the box below, so there was an ImageNet large-scale visualization challenge that was held way back, and then the VGG16 that you must have heard about was first proposed based on all those thousands of images that are available in ImageNet, and the VGG16 was the model developed by the University of Oxford researchers, and they fine-tuned that model and then try to, basically it takes a lot of time to train, but then they came out with a model, a standard model for you that is a pre-trained model to which you want to plug your images and retrain to get the newer weights. Okay. So this VGG16 layer had 16 layers, VGG16 model, 16 layer, 13 convolution, and 3 fully connected layer. And then, so that's it. So whatever frozen layers, that box, the dotted box that you see, is from the VGG16 model, the pre-trained model, okay, to which you give your set of images, right? And then the original layers of the VGG16 are frozen, and you start training your fully connected dense layer, dense network with your images. Therefore, whatever existing weight that were there, the FC1 512 and FC2 of size 512, that gets retrained with your set of images, right? So the ImageNet, one thing people typically object is that ImageNet doesn't have the medical images. Okay, it has all other like rivers, trees, hills, that kind of thing. General conventional images. They don't have medical images. So sometimes people question how can you get into a different domain, because medical image may have their own characteristics. But then we really did not find that a great limitation. So idea is that originally we did our own CNN model. We got some results. Then we started using the pre-trained models. I will show you what those models are. So that's the earlier one is a VDD16. This is a ResNet 50, which is quite popular. You find a lot of papers. And this has layers, 50 layers overall. And then it has various convolution blocks and ID blocks kind of thing. So pretty complex network. The problem with the VDD16 was a vanishing gradient problem was there, but that vanishing gradient is solved with ResNet 50, and therefore that became quite popular later on. Then MobileNet V2 version 2, another model, typically useful in an edge computing kind of environment. It's a kind of a lightweight CNN. Okay? So what we tried to do was, we tried to train our models with our images with all these pre-trained models and try to compare with our own CNN model and try to see which one was performing better. So if you look at the results, so on the right side box you see for inferencing we use 107 glaucoma, 140, I think 70% were training and 30% for testing. So typically these are the parameters that you use, like accuracy, sensitivity, specificity, and that kind of stuff. In F-score and MCC. MCC is a Matthews correlation coefficient. As long as it is positive and a high value, it indicates that your parameters are very sound and your approach is correct. What you find here, if you look at the specificity, specificity is one parameter that tells you about how many false positives could be there in your model, in your eventual output. So this low value indicates that there is a bias in the training. That means there are more glaucoma images than normal images during training. So therefore, that is not really acceptable. So with that kind of bias, I cannot really defend my accuracy of 93.75. So although in the early stages we had used our own network, we are not quite happy with the specificity value. So therefore, later on, we try to go around using the pre-trained models. Now, if you look at in the bottom box, you find the comparison with the pre-trained CNN models, VGD16, ResNet 50, MobileNet, and our own thing group. And then I said that our images are mild, moderate, and kind of thing. So for each of them, you can see the accuracies. You find that the deep CNN model in our case is doing very well with the mild ones and moderate ones. But then when it came to severe ones, the VGD16 seems to be doing better than our model. But again, we were not quite happy. It could be just a kind of a result that you cannot really defend based on the specificity value that you obtain. Okay? So, but still, overall, if you look at the accuracy in our case seems to be on a higher side, possibly because whatever earlier model that VGG and ResNet 50 kind of thing, they were not trained on the medical images. They were trained on other set of images. So therefore, it's possible that they report lower accuracies compared to the CNN model that we employ. So these are the kind of parameters that. So what we did was, additionally, we tried to compare with the existing literature to see how our model was performing. And you find that if you look at all those 9, 10, 11, 12 kind of references that are given at the end, each one, so the first one using a pre-trained model, pre-trained CNN. The second one was their own 18-layer CNN. They were not using the pre-trained model. And the third one, again, 2-stage CNN. And then fourth one, again, is their own CNN model. In our case, again, our own CNN model. And you can see that our model seems to be performing better compared to other, except that the second one, the reference 10, it is showing very good values for specificity, 97.39, in addition to accuracy and other things. But then they did not report F1 score and MCC, which are again very important parameters to defend your work overall. So therefore, if you look at our F1 score and MCC, we are quite comfortable over there. So which tells us that perhaps, because the other literature that I'm showing, they're all pre-trained on the, they're all trained on the existing databases, okay, like I showed earlier. So they were using those databases, which were clinical images, not controlled images. Okay, so therefore, there is also a possibility that, when you don't work in a controlled environment, you cannot really get accuracy that you're looking for unless, you have the kind of images that we have. So the next one is that, okay, you got certain results. How do you validate? How do you defend yourself? So for that, we use the visualization. So in the sense that look for features and see what features that CNN is trying to pick up, and whether the same features are what doctors also use when identifying certain images to be glaucomatous. So what you find on the left side, it is a glaucoma image. On the right side, if you can see, the cup and disc, which are important to us, are being picked up by CNN. And additionally, it is also picking up the blood vessels. Blood vessels are not important for us because they are not affected. If you are looking for retinopathy, diabetic retinopathy, that is where blood vessels come into picture. And again, on the right side also, so this is the convolution layer, 7th and 16th filter. So visualization, as you pass through the filters, you can actually see which layer is seeing what features. And we picked up these kind of layers in the first convolution layer and these filters. And again, in the last image also, you find that cup and disc are being identified. Blood vessels are also identified. And there is also what you call RNFL layer, retinal nerve fiber layer. And that is again, you see in the green color, right? In the background, it's also picking up. So we were a little worried because if it is giving high accuracy by picking up features which are not relevant to glaucoma, then perhaps that model may not be the right one to either use or validate. So that is one story I wanted to share. So we used our CNN. We are not happy with the specificity. When we try to visualize, it is picking up features that are not necessarily correlated with the glaucoma, and therefore overall we are of the view that the CNN model we try to suggest perhaps is not a right model to classify the fundus images. The second thing is the size of the images that we use. We used about 140, 137 kind of images. Such a small number, again, is not really good enough to train a deep learning network, and therefore you can't really expect high accuracies. Whatever high accuracies that I showed perhaps are because of bias in the training process. That's a kind of a, again, we could publish a paper based on that, but then, we are not totally happy with the result that we got. So, so as I said, we generate the synthetic images from the original image. So we have image transformation based, augmentation, and also we also use the GAN technique, DC GAN and fixed bit GAN, for augmenting our image. So overall images jumped from 135, 140 to 1500 or so. Okay. And we did the same with the normal and glaucomatous images. And then we do the pre-processing and pick up the ROI, which is the cup and disc region. And then we have a lot of data to show here. So we try to kind of compare with so we try to apply our model to the existing public data set also. Okay. So ITRIMA, Origa, Christie, these are public, and private is ours. So you can see the number of images, glaucoma and normal, total images, and image dimension. But then we don't take the complete image dimension because our region of interest is only the central cup to disk. Therefore, we take out that and reduce the size to 224 by 224 because that is a region of interest, as well as will help you to do your computation and classification faster. And we also on the if you the data basically models that we use learning model, there are hyperparameters, and then for each of the existing databases, the optimizer that we use, these are all basically the hyperparameters. And then we also used our own data set with certain hyperparameter values. So whatever results that we are going to show are based on this data, the training data that we have picked up for various sets of images. So the results tell you that now this is a little more validated data for me because now we set aside our own CNN model. We now started depending on the pre-trained models such as ResNet and BGG16 kind of thing. And then we started training them on all the data sets, public data sets plus our own data sets. And within our own data sets, we also try to compare two different augmentation techniques. And you find that VGG16, ResNet 50, and MobileNet and DCNN kind of thing, that original model that I was talking about. So you find that ResNet 50 with the DC GAN as the augmentation, as the giving us the highest accuracy, and also the related, later on I think I'll show you the related model metrics also. So this is one interesting result that we got. So this work actually went into IEEE Access journal. This is one thing that we talked about. So ResNet 50, which is a pre-trained model, was used in training the same thing with our own data set with DC GAN as the augmented approach. And then again, you can see here, DC GAN was to fixed GAN. So you find that ResNet 50 is doing very well in terms of the accuracy, F1 score, and also MCC. So these are all the simulation, training, testing, validation was done by us. We took those data and then retrained with these pre-trained models to finally arrive at which model is doing really better. So this work, after 3-4 iterations or so, it got reported in IEEE Access. So these are some of the things I wanted to show you, but you can see later on. But then important thing is, okay, ResNet 50 is doing very well. How do you validate? And this is where we brought the visualization back. Okay, so GradCam is one of the XAI techniques that is typically used for visualization, for explainability. So you find that, I'm not going to talk about all other things, but if you look at ResNet 50, so basically you have the original image, heat map, and then you overlay that on the original image to get your GradCam visualization of features. So you find that BGG16, the heat map is beyond the cup and disk, and also MobileNet also, it is actually going beyond your cup and disk. But what you find with ResNet 50 is that you have the cup and you have the disk, that surrounding area actually by the model. And similarly, so A is the furnace image augmented with the image transformation. Second one is with the DC GAN and fixed fix. So what you find here is that in addition to very high accuracy and other performance metric that we reported for ResNet 50, we are also able to explain that accuracy through this visualization images, where ResNet 50 is able to identify the fundus, core fundus up to cup and disk variations as compared to other models. So of course, this is the kind of thing, the process that you, the mathematical equation that you use in the training. So if you again compare, yeah, again whatever I said is reset here. So again, you see in the last row, pre-trained CNN, it is reporting very high, with our data, not with other databases. Yeah, I think time we are looking at. Okay, I'll just quickly take. So we didn't stop there with the CNN. We also went to the So transformers, as you know, proposed in 2017, and then typically they are used in NLP, natural language processing, and they became a super hit, and that is how you have ChatGPT and everything coming out. And my suspicion is that maybe next 2-3 years, Vaswani, right? Vaswani, the first author of the transformer paper, his team, possibly with Sam Altman and possibly with Jensen Huang, they may get Nobel Prize maybe in 2 years or so. That kind of amazing revolution that came out with all your transformer architectures. So transformer architecture originally for NLP was proposed in 2017. In 2021, another paper appeared that tried to apply the transformer architecture for images. Okay, that's called vision transformer. So we also tried to see the vision transformer apply, that architecture to other images. Kind of, it's a little tough to understand. You need to really go through. And this is the paper. So an image is 116 by 16 word, Dostoevsky and others. Transformers for image recognition. That is where the entire architecture explained very, very clearly. And we applied that architecture to see whether transformers do better compared to the pre-trained CNN models in terms of, so there is, you start with the image, you divide into patches, and those patches are projected, basically you flatten them and then project. And positional embedding, where the tool has to know which patch comes when, So that correlation among the patches is important. Therefore, positional embedding with tokens is done there. Then the transformer encoder is an important thing, and then the right box tells you how the transformer encoder works. And within transformer encoder, you have multi-head attention. And again, the right box, extreme box, tells you what the multi-head attention do. Okay. So this is explained very, very clearly. So you need to spend a lot of time to code all this. So one has to really depend on one's experience. And there is another model that is called shifted window. So in the case of transformer model, you have patches, each window is fixed. But swing model is where you keep shifting the windows, okay, across the image, those patches essentially. So that's a little more, again, this paper you can go through. You need to spend a lot of time to understand the whole thing. But point is that we try to compare, how the VIT model does as compared to CNN. And these are kind of data in terms of memory required, training time, kind of thing. But interestingly, within vision transformer, you have VIT, V16, 32, long 16 kind of thing. And we found that the VIT V32 performs very well, almost comparable to Resonate 50. Okay, if you look at the accuracy, sensitivity, specificity, and all, these are almost matching with the pre-trained model. But the question is now whether you can explain the results. Okay. So for that, again, we went for visualization, and we found that within transformers like vision transformer and swing transformer, with V32, you can see the middle image. If you look at the left image V16, it is picking up partly, but it is also picking up macular region. Macula has nothing to do with glaucoma, but it's picking up. So therefore, we know that it's not doing the right thing. But the middle one, which is VIT V32, to which the results I showed, 99% accuracy kind of thing, it is currently picking the cup and disc. And long 16 is actually shifting from the cup and disc. So therefore, we kind of conclude that perhaps V32, in addition to the high accuracies, it is also able to visualize the features that typically characterize glaucoma. So you have many other things that you can, and then we have the results that you can see later on. So this is the work that appeared in IEEE ANSYS. So you can see that VATB32 with GradCam visualization shows you accuracy, sensitivity, and area under the curve. Again, very good values. And FL score in the bottom box, you can see a very high value that show you that it's performing very well. It has validation in terms of visualization also. So several deep learning model visualization of features examined, and certain model turned out to be better than others. Important features are picked up, picked up by these models are considered. Therefore, if you want to do the glaucoma kind of classification, there is a strong case. ResNet 50 or vision transformers are strong candidates for glaucoma classification, which could possibly extend to retina and other things also. One final point I want to tell you is that when we use these models on the existing public databases, they did not give correct results. So, which means that it is. I'm not blaming those images, but maybe you need to kind of tweak your model to suit that data set so that you get higher accuracies. So, as you know, most of the deep learning is brute force, right? You have a model, then you keep on putting numbers and repeatedly carry out simulation till you get the result that you are looking for. Perhaps those public databases would need a slightly tweaked model, CNN or vision transformers, so that you get the accuracy that are required. Okay. So this is some kind of conclusion we could reach after 4 years of work looking at the glaucoma. So thanks so much for your patience and attention. Appreciate your thank you.
Thank you, Professor M.D. Srinivas, for wonderful insights on processing medical images. So now I request Professor Abdul Razak and Mr. Santosh Kore to present a memento to Professor Srinivas. So the next keynote speech is by Dr. Roman Daniel. He was born in Czech Republic. He received his speech degree in automation and control system in 1989, and the PhD degree in automation and technological processes at VSP, Technical University of Ostrava in 2002. He spent 18 years in commercial practice in the field of IT and ICT, and for 4 years ran his own company specializing in software supplies for industry from 2009 to 2012. He was an assistant professor at the VSP Technical University of Ostrava, Institute of Economics and Control System, and from 2012 to 2017, he was the head of automation department. Since 2012, he is a visiting professor for WSG University of Economy, Bydgoszcz, Poland. Since 2018, he is an assistant professor at Institute of Technology and Business, VST, Faculty of Technology in sorry, right? So this is here. Since 2009, he also holds lectures at VSP-TU Ostrava, Faculty of Economics, Department of System Engineering and Informatics. Dr. Donnell is a member of the ZEC Society for System Integration since 2010. His research areas include information systems and automatic control in industry, databases, IoT, operating system, programming languages, and software development. With this brief introduction, I welcome Dr. Raman Daniel for today's keynote speech. Sir, please, stage is yours now. Thank you.
So good morning. My name is Roman Daniel, and for this event, I prepare my speech about information systems and the data quality in the control of continuous production. So I was introduced, so I can skip my first slide. I want just emphasize that I spent 18 years in commercial practice making these systems, programming and do maintenance of databases, and I was participating in several projects considering with development of information system mainly in continuous production, but not only. And this is the reason why I prepare this speech when I want to present some experience that we received with working with different types of sensors. As already have been mentioned, I am affiliated with two universities. The main one is VŠTE, Institute of Technology and Business in České Budějovice. It's in the south of Czechia. And second one is VŠB, Technical University of Ostrava. It's close to Polish border, and it's in the place where I'm born. And I'm already sitting professor in Poland, in Bydgoszcz, WSB University, Polish speaking, so they used my ability to present some talks in Polish language. So I focused in my presentation on continuous production. I at the beginning want to a little bit explain why continuous production and what is specific for this. This main information system, mass category, so system for production control. It's crucial to understand that there are three completely different types of production, and completely different task is solved in these particular types. So first one, and the most common, is discrete production. This production is characterized that on the output of this production is a product. And this product could be identified by some number, some ID. So in this information system, the crucial task is to identify the product using some barcodes, QR codes, or RFID technology. And this system would provide so-called product lifecycle management. So we can collect information about history of production of every particular product. So via this ID, you can search when, where, and which employers make this product, so-called traceability. For example, in food industry, European Union required since 2005 traceability all products. So via barcode or RFID code, you can search all history of the food product. This is important for supporting standard that I mentioned here, ISO 9000. This standard is about quality control. So if you see somewhere ISO 9000, first word that should come in your mention is quality. And this standard requires to simplify two things. First thing that all production processes are documented. And second thing is that if someone make a product that the quality is low, it's possible to search why it's happened. And this is this situation that information system that provide traceability and product lifecycle management helps to requirements for these standards. And these standards is crucial if some company is certified via ISO 9000. For clients, it means that this company manage quality control. So some clients prefer a supplier that is certified according to this standard. And if this company has a proper information system that provides information about traceability, it's fit together the requirements of standards and information that are provided by this information information system. So this is a first time of production. Second time is continuous production. This production that I'm focused on. This production is completely different because on output there is no product but mass of something, mass of some materials, mass of energy. So it's mainly metallurgy production, some chemistry processes, working with electricity, with gas distribution. So the crucial task on this production is management of quality. And for information system, it means that there should be some possibility to measure quality parameters in real time to achieve that on dispatching level, some workers could do some activity to help the production process, and to do this, this operators needs information in real time. So last information system in post-production is real-time measurement of quality parameters using proper sensors and provide information to help controlling activity of people on dispatching level. Third type of production to finalize this summarization is batch production. It's a special type of production that is based on a certain amount of input materials is produced certain amount of output products with the same quality. The nice example is, for example, wine production. At the input is a big bin with wine, and the production makes, for example, 1,000 bottles of wine from this bin. And there's a second bin with the wine of the same mark, but quality could be different. And again, 1,000 bottles of wine with second bin, with different quality. So there is a batch number on this product, and if something happened and the quality is not good, they could put off all this batch according to this batch number. So for information system for this type of production, it's crucial that this system is working from input to output with batch numbers. There must be support for batch numbers. If some company buys a mass system that and has batch production, and this system does not support working with batches, this system is absolutely unusable for this type of production. So at the beginning, when we're making information system for production control, we should recognize which type of production is in the company and choose or make proper information system that helps the task that is crucial for this type of production. Also, I want to mention just one note. Maybe you noticed that the term Industry 4.0. In Europe, it's very popular, and this terms comes from Germany. I think the first it was used in 2013 in CB in Hanover exhibition. And the idea of Industry 4.0 is to make completely digitalization of all production processes, so everything should be automated on the level that humans work is almost avoid, and human do also only setting of parameters of the production. It's the ideal state. It's still not achieved, but it's the ideal state. And I want to emphasize that this Industry 4.0 comes from discrete production, and mainly automotive is connected with this terminology. And in continuous production, application of Industry 4.0 principles are very rare because this production is really different. So if you somewhere see Industry 4.0 solution, probably it is focused on discrete production. So to summarize about continuous production, the specific is that output is a material, not a product. It's very often operated in 7 to 24 modes, so it's continuous, and it could be continuous for a long term. If you have in mind foundry, for example, it could work many years in continuous mode. Crucial task is to evaluate, monitoring quality of products in real time. And in information system, it's also about energy consumption, because 2 years ago in Europe we had energy crisis. That the prices of electricity was very high. So at this moment, a lot of companies start thinking how to save consumption of electricity, and some information system would help with this, for example, monitoring time of devices is running and how many times devices start and stops, because the start of some devices is a situation that the most electricity is consumed. So if some devices is started and stopping again and again, this exactly thing that we can save electricity if we solve this situation and remove this high amount of starting process. And when we're making information system for production control, we need data about this production. So we use sensors. And now I want to speak about problems that we found working with this particular type of sensor. I suppose everybody, you know that there are three types, different types of sensors: analog, binary, and incremental. Analog measures some physical value like temperature, moisture, pressure. Binary is two-state logic, so something is running, something is stopped, something is open, closed. So there is an information 0, 1. And incremental is special type of sensors that count some pulses that are equivalent some amount of values. So, for example, gas in pipeline, it's measure how many gas comes through hour, for example. So you should have two values and should calculate current value minus previous value, and you obtain some value about gas flow or oil flow. Or you can use these incremental sensors in as a weight that, for example, loading of some material on wagons. And there is a tensometric weight, and every kilos making some pulse. So the sensor count the pulses, and it is equivalent of how many products is loaded into the wagon. All these sensors has specific problems. So we do analyze the most common problems. To summarize it, with analog sensors, it is about proper sampling, but it's about proper analysis of technological process. But the main problems that we find is aging of the sensors. So there is some physical principle of measurement, and within time, the characteristics of sensor element changes, and the sensors start producing information that is not correct. So we need to solve this. With binary sensors, the biggest problem is to manage how many information is written to the databases, because sometimes some process has no information that is valuable for collecting. For example, some conveyor belts is running for several hours. It's not necessary to write every second that the conveyor belt is running. It's cost a lot of information to the database with no values. So we should solve this, and the best solution is to write down into the database only changes and prepare some scripts or some calculation process that renew state of the devices in a given time. And incremental sensors are very specific. I show you on one case study what is the biggest problem with this sensor. So the case study that I provide for you is from Energy company. It's a German company that operates in many countries in Europe, and it's responsible for gas distribution. They operate several bins, and one of the bin is in Czechia. It's in location in Černovice, close to Slovak border, and there is a big underground gas storage. It's a not artificial build. It's a natural gas storage. It's a specific rocks that has ability to gather some gas inside. So this bin is used that during summer consumption of gas is very low because it's good weather. So they inject the gas into the bin, and during winter, where it's low temperature and everybody use gas for heating, they exploit the gas from this bin. So there is a quite complicated technology that operates with this gas and manage quality parameters like moisture and other parameters of the gas. So there is a pipeline, and in this pipeline there is several types of incremental sensors that measure how many gas goes through the pipeline. And first problem with this sensor is that this sensor do not distinguish if it's explosion or injection. They just continuously measure and increment the value. So the measurement should be connected with some another process that distinguish what is the operation mode of the bin. But the biggest problem of this measurement, there is a architecture of the measurement, and my part was this second and third row. So from SCADA system is connected to sensors, is produced some flat files with completely information about measurement every hour and in every change of operational mode. My process collect these files and write down into the database history of gas flow and changes, and storage procedures in database calculates balance value. So how many gas comes through 1 hour per shift, per day, per decades, per month, per quarter, and per year. And there is a visualization layer for managers for dispatching. And the problem is that sometimes technicians on this technology do maintenance work. So someone comes to the lines, disconnect it with the bin, and do some testing. But the incremental sensors continue with counting the value. So after this maintenance work, absolutely different value appears on these sensors. And if this calculation is in automatic mode, in this moment, the procedures that calculate balance value calculate absolutely nonsense, the value that is technologically impossible. So this is a very special type of problems, and in this calculation, it should be managed and it was not easy task to do this, because this maintenance work are from a point of information system absolutely random. So there is no possible to do some tables with times where it happens. It's just random disturbance of the calculation, and it takes a while that we manage this randomly behavior of this. The second problem, and it's very strange, is connected with daylight saving times, because I don't know if in India and in Dubai, but we move time every spring and every autumn to summer is 1 hour more, and in winter we go back to the standard time. So in spring, 1 hour is missing, and in autumn 1 hour is more than should be inside the 8-hour shifts. So again, and it's every year in different times. So again, this is a quite problem how to manage it in automatic mode. We solved it that we prepared a special table that we manually put the date, this time is changed, and which hour, and the calculation process should look at this table and manage the situation. So working with this mental sensor is really very specific. Okay, second case study about specific situation working with sensors is from coal preparation plant, and this situation is about analog sensors. In coal preparation plant, I don't know if you're familiar how it works. Coal that is exploited has different quality, variable quality. And customer, of course, do not want variable quality, they want stable quality of the product. Especially metallurgy processes are very dependent about ash content. If ash is something that remains if you burn the coal. And the more ash is inside, the less energy is received. So metallurgical processes needs ash content maximum at 10%. If it's higher, it's bad for metallurgical processes because energy is not sufficient for these processes. So before coal mine company sells the coal to the metallurgical company, they have to do some preparation processes to stabilize amount of ash content. And there are several technologies that allows manage this ash content. Heavy liquid, jigging, and flotation. In my picture, there is a flotation in the picture in the middle. It's a device that is used for flotation. Flotation, just in one sentence, means that coal is put into the water, and this coal must be crushed into the fraction to maximum size 3 millimeters. So it's a dust, and it's put in the water. They add some oil called floater coal, mix this, and the grain of coal is filled to the oil and go to the surface as a foam. So later this foam is collected, dried, and you receive coal without rocks, so without this ash content. So by this technology, there is a classical PI controller and ash meter on the output that in real time provides information about real ash content in the output, and controller, according to this information, add more floater coal or add more water if there is a too low and content of ash, because it's economy. If metallurgy wants 10% at maximum, coal company should not provide 5% because it's too quality, and the company lost. So the ideal content is 8 to 9, slightly before 10, but not too much. If it's too much, they artificially add some amount of rocks to sell the biggest amount proper price. So it's very important to have this information from these sensors in real time to allow automatically control this. So operator just said, I want maximum of 10% of hash content, and all the things are automatically managed by a controller that is connected with a real-time hash matter. This hash matter is quite complicated devices because you are measure hash content on a running conveyor belt. So it's not possible to take some samples and do laboratory analysis. It must be on the running material done, and the only method how to achieve this is hash method that used radioactivity. There are two radioactive sensors, americium and cesium, and the radioactivity comes through layer. And behind the conveyor belts is a simulation probe that collect how many radioactivity comes through the layers and calculate the hash content in real time. So this device is very complicated, and only authorized person could do some maintenance activity with these devices. And the problem is that the sensors, after several years, change the physical parameters and start showing improper value. So every year should be verified with Ethalon to certify that the measurement is still in good quality. So this is a problem that we meet with this sensor, and we try to detect automatically that the sensor is still working well. So sometimes, and I mean every day, every 2 days, they collect some small sample of the hole, do laboratory measurement, and compare it with the hash map shows. And if several times within several weeks there is a significant difference, it means that the sensor starts showing improper value. So at this moment, the company should start thinking about checking it again against Ethalon, and in the worst case, remove this hash method from operation and do new one. And last one that I was speaking about is, because this conference is focused on modeling, so we also start to thinking about using so-called digital twin. It's a digital representation of some processes. Again, these digital twin are quite popular, and a lot of companies starts providing this technology, but mainly they are also focused on discrete production. Continuous production is very rare that some companies able to prepare proper digital twin, because it's need that the model really represent the physical process. And preparing of digital twin is not easy task, and it's very the costs are very high. So again, economic. You should calculate if amount of money that you put into making this digital twin is enough to make profit, because sometimes it's question what you receive if you use this digital twin. You can simulate some what if scenarios, for example, test new configuration. In this, impossible to do some test in a production line because it's operated in 7 to 24 modes, and it's not able to do testing. So in this moment, digital twin is useful, and nowadays we are start thinking about making some digital twin for continuous processes like coal mining or some metallurgy processes. I also I'm involved in some systems for metallurgy company. So as a conclusion, this is an area or research project that we are doing. For example, we start to try intelligence tool to the analysis of defects in welding robots. It's a new project that has been started in October 2025. So we We have no result yet, but we are expecting that artificial intelligence help with automatic detection of improper welding. Of course, Industry 4.0, digital twins, some using of drones in agriculture. We had a project with Palestinian University in Jericho to detecting some effects of crops, and we are also making model that predict salinity of the soil in date palms. So a lot of project yes, also if some of you are interested in cooperation, we are open. And at the end, I want to thanks Mr. Santosh Gore and Sci Information Solution. We are cooperating with him, and my presence here is a result of this cooperation. So many thanks to invite me to this conference. Thank you.
Thank you, Professor Raman Daniel, for a wonderful speech on automatic control system. So now I request Professor Ale Selvi from Triple Department and Mr. Santosh Gore to present memento to Professor Raman Daniel. So I'm requesting all delegates to join for high tea in the next room, G08, please. After that, sessions will start at 11 in respective session rooms. Thank you for attending.
That's good, but we'll have some photograph here. Sir, we'll have group photo. So can we join for a group photo? For a photo. Everyone, yeah. Everyone. Volunteers like can. All delegates, please can you join for group photo? Group photo. So remember, you can come on the stage. Okay, Aditi, can you take a photo? Yeah. Sorry. This side. After you. And here. Small. Nice. Thank you so much. All students can join. Please. Yeah. Yes. Okay. Thank you. Thank you. Thank you. Thank you. Can we stable food? Yesterday we didn't get. But how is to get that installation? What's the thing? Sir, could you please switch on the background for a while? Okay.
There's a drive, we'll upload it.
Yes.
Yeah.
I'll share it.
What's the name? I forgot.
It's okay, sir. Aditi.
Aditi. Adi. Not Aditi. A-double-A.
Yeah. Sir, actually, I took all the pictures and videos on your phone.
Okay, I'll share this. Yeah. Fine, thank you. And what about yesterday's photo, like from where I can get the?
It is, we put everything on a drive and we share the whole drive.
Okay, by today, can we expect today?
No,
Because many tests are asking.
yeah, usually at the end of the.
Okay.
We share the drive, I mean, whoever wants it can access.
Yeah.